Alright, so now we have seen some basic definitions and some more advanced definitions of graphs. So you might start wondering, what are interesting examples of graphs? Is this just an empty notion, or do there in fact exist graphs in real life, so to speak? And the answer is, of course, there exist graphs, otherwise this course would have been quite pointless. So in this video, we're going to go through a few important examples of graphs, certain types of graphs that are common and that we should all know. So we start with the most trivial example, and that is null graphs. So a null graph, from German null, meaning zero, is a graph where there are no edges. So this graph has only vertices and no edges, and therefore there is only one graph for each number of edges. And the notation is NN. That's the null graph with n vertices. Sorry, not edges. So, for example, N3 would be just this graph with 3 vertices. So, not a very exciting graph, but still it's important to have knowledge of the trivial notions. So, this graph is completely determined by the number of vertices it has. On the opposite side, we have complete graphs. So these are graphs which are simple, but have as many edges as possible. They are called complete because you simply cannot add edges while still keeping a simple graph. Remember, simple graph means you have no multiple edges and no nodes. And this graph is written or denoted Kn, the complete graph with n vertices. So if we look at, for example, K3, now we have 3 vertices and all possible edges without double edges or loops. So this is K3. And then you have K4. K4 has 4 vertices. And now you draw all possible edges. So from each vertex, you have edges to all other vertices. This is one way of drawing it. Another way of drawing it, so this is the same, or rather isomorphic, if you want to be pedantic, but let's not. So there is no reason why I would draw these edges as diagonals. I can draw one going here and one going, well, let's put that a diagonal. So there are many ways to draw the same graph, but the edges go between the same vertices, and in this case, from each vertex, there is an edge to every other vertex. Let's test our understanding. So pause this video to go back and revise the definition of the complement of a graph, and come back to answer the question, what is the complement of the null graph, and what is the complement of the complete graph? Okay, so let's look at the answers. So if you have, for example, N3, that's this graph. Now to get the complement, I will draw all the vertices, all the edges that are not there, and erase all the edges that are there. So there are no edges to erase, and I simply add all vertices. So this is the complement of N3, which is the complete graph on 3 vertices. And in general, the complement of the null graph is the complete graph on the same number of vertices. So now, what is the complement of the complete graph? Well, you do the opposite thing. You take the complete graph. Now there are no edges to add, but you erase all edges that are there. You get the null graph. But instead of reasoning like that, we can argue as follows. So the complete graph bar, well, the complete graph was the complement of the null graph. So it is the null graph bar bar. It's the complement of the null graph. But as we saw earlier, as you had an exercise to show, or to find out what the complement of a graph is, the complement of any graph is the graph itself. So it is NN. Because to get the complement, you erase the edges that are there and add the edges that are not. And if you do that once more, you get back the edges that you had from the beginning. Next question. What do you get if you take any simple graph and join together the edges of its complement? So let's look at an example. Let's look at this graph. So this is a graph on 4 vertices, and I have these 3 edges. Now, if I add the edges of the complement, so these are the edges that are not already there, to make a simple graph, well, then I get all possible edges, right? Because I had the edges that are there, and I add all the possible edges that could have been there to keep a simple graph. And so G together with the edges of G bar is Kn, where n is the number of vertices. So you get all possible edges. And that is true for any simple graph G. Second question. Let's look at the complete graph now. How many edges does it have? So pause and think, maybe draw a table with the first few cases, and we'll go back and look at the answer. Okay, so the answer is, well, how do you calculate this? So you have, how do you draw a complete graph? So you draw the number of edges, then from each, you draw the vertices, then from each vertex you draw edges to every other vertex. So you have as many edges as the number of vertices times the number of other vertices. So I do this here, do this here, do this here, do this here, but then that gives me a double count because each edge will have been counted twice because each edge has a start and an end. So for example, from this vertex, I have an edge here, and an edge back to the first vertex, but I already had this edge. So because each edge has 2 endpoints, I'm dividing by 2. So the number of edges in Kn is n times n minus 1, altogether divided by 2. So null graphs and complete graphs were the 2 extreme cases of graphs. Let's look at some intermediate cases. So one graph that's very common is a cycle graph. So a cycle graph is a graph that is connected and each vertex has degree 2. So, and the notation is Cn. So let's look at C4. So I have 4 vertices. Now this vertex has degree 2, so this means that it has 2 edges into it. Same here, and then this has to go back here. So it is a cycle. A more reasonable way to draw this graph is something like that. And notice that just like null graphs and complete graphs, cycle graphs are determined by their number of vertices. So there is only one cycle graph for each number of vertices, and it has the same number of edges as vertices. Note also that the graph Cn is simple when n is greater than 2. So C1, well, there you have a cycle with 1 vertex. It is a loop, and C2 has a double edge, like that. From cycle graphs, you can create path graphs. A path graph is simply a cycle graph where you have erased 1 edge. So for example, let's look at P4. So you start with the cycle graph from earlier on 4 vertices, and you erase one edge. So it doesn't matter which edge you erase, because somehow all edges play the same role in a cycle graph. So if we maybe erase this edge, then you get a path, what you would imagine is a path of length 4. But we could also just as well have erased this edge, and we get an isomorphic graph. It's a graph where all vertices, it's connected, all vertices have degree 2, except for 2 so-called end vertices that only have degree 1. Another thing you can do from a cycle graph is to get a wheel graph. So you start with a cycle graph on one vertex less, and you add sort of a vertex that is adjoined to every other vertex. So what does this mean? So let's try to create W6. So you start with C5, the cycle graph with 5 vertices. And then the most practical thing is to draw this 6th vertex in the middle, and it's connected to every other vertex. So you get something that looks like a bicycle wheel, where you had the outer wheel, that was your graph, and you then put the center point of this graph. So wheel graphs, just as path graphs and cycle graphs, are determined by the number of vertices.